All right. Well done. Jesus Christ. How's everybody doing? Can you hear me well? We'll wait a few minutes till everybody comes in. All right, how are we doing? Sorry, we had some technical issues this morning. Isn't it always the case? I'm running an old computer, and it is what it is. It's all good. So we're here. Let's get to it now. A few things. You'll notice that there is a small lag, probably 15-second both ways. So if I ask a question and you answer, it takes about 30 seconds for me to get it back. So I mean, again, it's fine. And I feel YouTube is the best delivery system so far. So we'll go with that. We were looking at partial fraction decomposition. So we introduced that last time. Let's take a few examples. Here, they're only asking us to decompose this using partial fraction decomposition, not to actually solve for the coefficients. Although, well, we'll see. Maybe we'll solve here just for fun. So as you know, the idea is to decompose it. Well, first of all, observe that the numerator, right, this is a rational function, with the numerator having a smaller degree than the denominator. So we're good to proceed. Let's factor the denominator into irreducible polynomials. This factors nicely as the difference of squares, x squared minus 1, x squared plus 1. And the x squared minus 1 factors again as x minus 1, x plus 1. Where x squared plus 1, we've seen that before. We had convinced ourselves that this was an irreducible polynomial. So these two being polynomials of degree 1, irreducible. And then the third one here, x squared plus 1, polynomial of degree 2. So may or may not be irreducible, but you look at the roots and they're complex roots. So partial fraction decomposition tells us that this factors, or that this decomposes as, right, polynomial of degree 1. So we search for polynomial of degree 0 on top. And you continue until you've exhausted the power, but it's already done. Then b over x plus 1. Right, similarly, polynomial of degree 1, so polynomial of degree 0 on top. And finally, polynomial of degree 2 here, so polynomial of degree 1 on top. Take a moment, rewrite that over a common denominator, and then we'll equate the numerator. Right, so this is a x plus 1, x squared plus 1, plus b x minus 1, x squared plus 1, and finally cx plus d times x minus 1 and x plus 1. The whole thing over the original denominator. Somebody's asking, can we decompose x squared plus 1 into x minus I, x plus I to find partial fractions? Well, I mean, you're suggesting that this is going to generalize to complex numbers, and indeed you could. And everything generalizes absolutely if you allow a b, well, so in that case, x minus I, x plus I might decompose into c over x minus I plus d over x plus I, which is exactly why this decomposes as cx plus d. Because if you were to put everything back over a common denominator, you'd see exactly this form. Short answer, yes, but we're not going to go into complex numbers. So let's stick with that. But your suggestion is exactly why this works, because everything generalizes to complex. So there you have it. We've put everything back over a common denominator. Then you would equate the numerators, and you can solve for A, B, C, and D. Seemingly going to be a lot of work here, so maybe let's not do that. And the question wasn't asking us to do so. So let's stop here. We move on to the next one. Again, the question is the same, just asking us for the form of the partial fraction decomposition. It's telling us not to solve for the constants. And again, before we tackle anything, let me point out, numerator has degree. You know what it is. And if you were to multiply that out, the denominator would have degree. Right, numerator has so denominator would have degree 5, and the numerator has degree 4. So the numerator is of lesser degree than the denominator. So we're again in the partial fraction form. We're good to go. There's nothing for us to do except decompose the denominator into a product of irreducible polynomials. Now this x cubed minus 1 has degree 3, so you know it's not irreducible. And you can spot a root right away. So x equals 1 is a root of x cubed minus 1. So x minus 1 must be a factor. Right? I mean, I don't know how x cubed minus 1 factors. Some of you might know. I mean, it is a difference of cubes, so you do have that formula, but you don't have to remember it, because you can always take a moment and do some long division. And let's do that right away. X minus 1 into x cubed minus 1. I've left some room here because I'm going to put some placeholders. There's no x squared, and there's no x. So we ask the question, what must I multiply to x to get an x cubed? And the answer is x squared. And you get x cubed minus x squared. And when you subtract, you get an x squared. Bring down the next term and repeat. What must I multiply to x to get an x squared? The answer is x. Subtract, getting an x, bring down the last term and repeat. What must I multiply to x to get an x? The answer is 1. You get an x minus 1, leaving you with a remainder of 0. And consequently, what does that mean? That means that x cubed minus 1 factors as x minus 1 times x squared plus x plus 1. Of course, you can check your answer. Check that this is correct by expanding that again, making sure that you get the x cubed minus 1. Now, before I forget, since I was having technical issues, and that's why we started a bit late, should the feed stop for any reason before 11:30, I'll try to get it started back again. So, because I mean, sometimes especially if there's a power failure or whatever other reasons, this could happen. All right, so what? Of course, x minus 1 is irreducible. It's degree 1. What about x squared plus x plus 1? So this is irreducible. And what about this one? If we look for the roots, negative b plus or minus square root of b squared minus 4ac over 2a. The discriminant here is negative, no real roots, so this is irreducible as well. And so the original x to the 4 plus x plus 1 over x cubed minus 1, x squared minus 1, this factors as x minus 1, x squared plus x plus 1. This factors as x minus 1, x plus 1. So you see that you really have two of the x minus 1s. There it is. So we've decomposed the denominator into a product of irreducibles. Now, partial fraction decomposition. Partial fraction decomposition tells us that this should decompose. Look at your first one. Irreducible is x minus 1, which has degree 1. So a over x minus 1. And you continue until you've exhausted the power. Here, power 2, so we're not done. B over x minus 1 squared. Some people were asking, why is it b? Why is it degree 0 since the denominator has degree 2? Well, it's the irreducible that's important. And the irreducible polynomial has degree 1. So a over x minus 1 plus b over x minus 1 squared, and now we have exhausted the power. You move on to the next irreducible polynomial, which is a polynomial of degree 2. So cx plus d and it was just power 1, so we've already exhausted the power. Move on to the next polynomial, which is a polynomial of degree 1, so e over x plus 1. Again, you would put everything back over a common denominator, equate the numerators, and solve for a, b, c, d, e. Seems like a lot of work here. Let's not do that. Instead, let's consider this. Again, a rational function, one polynomial divided by another, except that in this case, the numerator has higher degree than the denominator, right? Partial fractions tells us what to do when the numerator has smaller degree. Here it's bigger than or equal to. Leo's asking, where does the a over x minus 1 come from? I mean, you've decomposed your denominator into x minus 1 squared times this times that. So the irreducible polynomial is x minus 1, and you've got two of them. So a over x minus 1 and b over x minus 1 squared. How would fractions look like if it was x minus 1 cubed? Dan is asking, and he has given us the answer. The b term, b over x equals, I'm assuming that shouldn't be there. So it really should be b over x minus 1 squared, as pointed out, plus c over x minus 1 cubed. Exactly. You want to exhaust the power, and that's exactly what you did there. What is the greatest degree polynomial we would have to decompose since we have not learned matrices? Well, you don't need matrices, right? Matrices are a nice way to solve these, but they're not the only way, right? If you have 3 equations, 3 unknowns, you can solve that without using matrices. You isolate for one, substitute it in the other, isolate for another, substitute it in the third, solve, and back substitute. Nothing wrong with that. So all that to say, there's no reason for you not to have at least 3, if not 4, variables to solve for. But back to this example, where the denominator is of higher or equal degree than the denominator, and as I suggested last time, what you want to do is start with some long division. So let's do some long division. X to the 6 divided by that. So what must we multiply to x squared to get an x to the 6? And the answer is x to the 4. And then you subtract, getting a 4x to the 4. And repeat, what must I multiply to x squared to get a 4x to the 4? The answer is 4x squared. Subtract again, getting a 16x squared. And the question is, what must I multiply to x squared to get a 16x squared? The answer is 16. You get a 16x squared minus 64. Subtracting gives us a remainder this time, right? A remainder of 64. So what does that mean? Well, that means that this is equal to x to the 4 plus 4x squared plus 16 plus the remainder over the divisor. Right? I mean, again, for those not that comfortable yet with long division, let me convince you. If you have something like 112 divided by 5, right? What do? You say 5 into 112. How many times does 5 go into 11? It goes in twice. Subtract, bring down the 2. How many times does 5 go into 12? It goes into 12 2 times. And you get a remainder of 2, and you stop when the remainder is less than the divisor. Here you stop when the degree of the remainder is less than the degree of the divisor. And what does that mean? 112 divided by 5 is 22 plus 2 over 5. Right? Because if you put everything back over a common denominator, this would be 110 plus 2 is 112. And that's exactly what's happening here. Right? So this is that plus that. You can convince yourselves again by putting everything back over a common denominator. Common denominator being x squared minus 4. See what happens. But the point is, this is equal to that, and now when you look at this, you can apply partial fraction decomposition. Here we're in the proper form where the numerator has smaller degree than the denominator. Degree of the numerator is 0, degree of the denominator is 2. So here we're good to go. So 64 over x squared minus 4. Well, x squared minus 4 decomposes clearly into x minus 2, x plus 2. Polynomials of degree 1, so you know they're irreducible. And partial fraction decomposition tells us that this is going to be x minus 2 plus b over x plus 2. Can we read off 4, 32, 16, I want to say 16. 16 over x minus 2 minus 16 over x plus 2. Looks pretty good. Right? When you get good with partial fraction decomposition, you'll be able to read off what the answer is. So here, put everything back over a common denominator. Gemma is asking where the 16 comes from. Well, I mean, you got to solve. You got to solve. What am I talking about? Right here, you would put everything over a common denominator. So a times x plus 2 plus b times x minus 2. And that should be equal to 64 over x squared minus 4. So you have a times x plus 2 plus b times x minus 2 should be equal to 64. And now, I mean, you know, you have two approaches. You can expand and equate the coefficients, or you can choose a good value of x. In particular, if x is 2, this disappears, so you get 4a is 64. So a is 16. And if x is minus 2, this is gone. So you get minus 4b is 64. So b is negative 60. Exactly as predicted. How are we doing? Questions here? All right, so let's see how this helps us. Why did you only do the decomposition on 64 over? Well, everything else, I mean, imagine so So what do I want to say? Partial fraction decomposition is when you have rational functions, right? One polynomial divided by another. Now, that first part was just a polynomial in its own right. So there's no decomposing that. And imagine yourself in the context of an integral. If you were integrating the polynomial plus 64 over x squared minus 4, the polynomial in the beginning is easy to integrate. So it's only the 64 over x squared minus 4 that you need to worry about. Do you not run into any issues with x values not being divisible by 2 or minus 2? A valid question, right? Because here, you're not allowed to plug in 2 or minus 2. And then when you equate the numerators, suddenly you're plugging that in without issue. It's a valid point. It's a valid point. But if you're looking at this, here you have one polynomial equal to another one. And there's no... And then this is unrestricted by whatever happened before, right? This polynomial is defined for all values of x. So there's no issue. I mean, of course, if you are keeping track and you're thinking to yourself, here x is not plus or minus 2, so that carries over, it's a valid point. But just viewed as polynomials, which are defined everywhere, you're good to go. So the original inequality, does the original inequality ignore the whole after the division is complete? It doesn't. It doesn't, because your original function, which was x to the 6 over x squared minus 4. This is not defined at plus or minus 2. But when you do partial fraction decomposition, I mean, I forget the answer we had here, but something like x to the 4 plus 4 x squared plus 16, I'm going to assume. And then we said plus 16 over x minus 2 minus 16 over x plus 2. I believe that's the answer we had. I don't have it here anymore, but the point is, this function was not defined at plus or minus 2, and this function is still not defined at plus or minus 2. So we're not ignoring anything. The domains still agree. But as you pointed out, it's when you're solving here and you're plugging in these bad values that the domains don't agree anymore. But it's not really a big deal because this is a polynomial defined everywhere. All right, back to this. So you see what's happening, right? I mean, you have this this integral, which might be difficult to deal with if not for partial fractions, right? I mean, what would you do here? You might have to factor you might have to complete the square in the denominator, make a trig sub. Looks like a lot of work. Luckily for us, though, partial fraction decomposition to the rescue. The denominator factors easily as x times x minus 4. And originally, you had a degree 1 over degree 2. So you're already in partial fraction form. You're good to go. So this decomposes as a over x plus b over x minus 4. Put everything back over a common denominator. And equate the numerators. And we've already done the trick where you plug in good values of x. So why don't we do the other one? Namely, equating the coefficients. Right, so if you expand this, you get ax minus 4a plus bx equals x minus 12. Or a plus b times x minus 4a. So now coefficient of x on the left, a plus b. Coefficient of x on the right, what is it? Coefficient of x, thank you, 1. Constant on the left. Constant on the left. Constant on the right. So here it's easy to see that a has to be 3. And if a is 3, then b is minus 2. And there you have it. So this integral which would have been difficult. Why does a plus b have to equal to 1? We are equating the coefficients. Coefficient of x on the left, coefficient of x on the right. There's nothing mentioned here. You understood that it is 1. Right, so back to this integral then. Which would have been difficult, right? I mean, I think we convinced ourselves that completing the square and making a trig substitution would have had to be done, if not for partial fraction decomposition. But luckily, partial fraction decomposition tells us that this is 3 over x minus 2 over x minus 4. And now the integration is so easy that you can do it in your head. 3 ln of absolute value of x minus 2 ln of absolute value of x minus 4 plus an arbitrary constant. How are we doing here? Questions? Consider this. Notice that the numerator has the same degree as the denominator. Partial fraction tells us I'm not sure what HA equals 1 refers to. But here, exactly, thank you, Hunter, right? The degrees are the same, so we have to start with long division. So let's do some long division. What must we multiply to x squared to get a 3x squared? Of course, the answer is 3. And when you subtract, Olivia is asking if partial fraction decomposition is easier than trig sub. Is there any time it would be better to use trig substitution? Or should we always use partial fraction decomposition? Well, if you have something like this, then you have no choice but to use trig sub. So if a question can be answered using trig sub or partial fraction decomposition, you want to do whatever's easiest for you, right? All partial fraction decomposition is doing is it's giving you options. Sometimes you have no choice but to use trig sub. And sometimes you have to use partial fraction decomposition followed by trig sub. I'm sure we'll see some examples of that. So what have we done? This is now 3 plus the remainder over the divisor. Right, so this 3 is easy to deal with. You know how to integrate 3. So really the question is, how do we integrate that? And on that, we're going to apply partial fraction decomposition. How does the denominator factor? Into a product of irreducible polynomials. You know exactly how that factors. Thank you, Amir. And now, these are irreducible polynomials of degree 1. So partial fraction decomposition tells us to search for a over x plus 2 and b over x plus 1. Put everything back over common denominator. And you can equate the numerators. A times x minus 1, b times x plus 2 should be equal to minus 3x minus 4. Let's plug in some good values of x here, right? I mean, we have 2 approaches, whatever you want to do. Both should yield the same answer. When x is 1, a is gone, and you get 3b is minus 7. So b is minus 7 over 3. And if x is minus, Sorry. This should have been a plus. So you don't want x equals 1, you want x equals -1 to get rid of that. And when x is -1, you just get b. b equals -1. Thank you, Olivia. Sammy, thank you. And when x is -2, that's gone. So you get -a equals, this is 6 minus 4 is 2. So a is -2. So this integral is 3 minus 2 over x plus 2 minus 1 over x plus 1. And you see how easy these integrals are. Can you show how to do it with the other method as well? We did that in the previous question, but we'll do it again in the next one. I am at home. This is a blackboard that I constructed for the pandemic, knowing that we were going to be online for a while. Let's finish that up quickly. Antiderivative 3x minus 2 ln of x plus 2 minus ln of absolute value of x plus 1. From 1 to 2. So this is 6 minus 2 ln 4 minus ln 3. Subtract, plugging in 1. 3 minus 2 ln 3 minus ln of 2. So finally, the answer is 3. You've got 2 ln 3 here minus ln 3, so that is plus ln 3. Ln of 4 is 2 ln 2, so that's a minus 4 ln 2. Plus ln 2 is minus 3 ln 2. How are we doing? Questions here? Questions? Anybody? Still a little confused how you derived A and B values from that. We were plugging in good values. So I've rubbed it off now. But looking back at this, observe that if x is -1, if x is -1, this is going to be 0. Right? The idea is that this equation should be valid for all values of x. So if you choose good values of x, that might help you solve. And when x is -1, this is 0, this disappears. So in the first one, I was plugging in x equal -1. This is gone. -1 plus 2 is 1, so you just get b on the left. And when x is -1, you get 3 minus 4, which is -1. So you see we have b immediately, just by choosing one good value of x. And similarly, if you choose x equals -2, the b term disappears. So you get -2 plus 1, which is -1, so you get -a on the left. And when x is -2, you get 6 minus 4, which is 2. What happened to the ln 4 in the last problem? Ln 4 is ln of 2 squared, which is 2 ln 2. By properties of the logarithm. By properties of the logarithm, you can bring the 2 down. So we get -4 ln 2 here. But we had a plus ln 2. So we get a -3 ln 2. Convinced? I'm sure you decomposed this according to partial fraction already. Did you? Right, and how does it decompose? Right, x squared plus 1 is the irreducible polynomial here. Right, and the denominator would have degree 4 if you expanded it out. So numerator has degree 2, denominator has degree 4, we're good to go. So how does partial fraction decomposition tell us that this decomposes? Partial fraction tells us that this decomposes as ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared. Very nice, Amir. Thank you. Amir has given us the answer, telling us that a is 0, b is 1. C is 1 and D is 0. Why can't we decompose it? Right? Why can't we decompose it that way? Well, observe that if we go with your decomposition, which is ax plus b over that plus cx plus d over that, then the denominators are the same. So you could rewrite this as a plus cx plus b plus d over x squared plus 1. And now, so first of all, you wouldn't need this extra term because this has this form already. Moreover, this one has a square in it. So, right, so first of all, this would give rise to that, which is essentially this. So now we're asking, why is this not equal to that? Well, when you multiply the whole equation by x squared plus 1, you'd still have a denominator here and none over there. So, very well, I think you're convinced. And So partial fraction decomposition tells us that the decomposition should be this, and then you can put everything back over a common denominator and solve for A, B, C, D. But let me point out that partial fraction decomposition is unique. So if you have a partial fraction decomposition, then you have the partial fraction decomposition. And sometimes you can just read it off, as is the case right here. Can you see how Amir came up with the answer so quickly? By decomposing the integrand into two fractions. Right? Grouping these two together and the x separately, you get this. And now x squared plus 1 over x squared plus 1 squared is just 1 over x squared plus 1. Isn't A 0? It is. It is. A is 0, B is 1, C is 1, and D is 0. How do you know to group them like that? Well, right, Amelia is asking. Experience. Playing around with partial fractions. Seeing things, right? I mean, the point is, if you group the x squared plus 1, you get the denominator. And Hunter is asking how we were able to find ABCD without plugging in. Well, this is it. This is it, right? By grouping appropriately, you end up with this. And now it's important to observe that this is in partial fraction form. It's not obvious, right? But 1 over x squared plus 1 happens when A is 0 and B is 1. So you have the 1 over x squared plus 1. And x over x squared plus 1 squared happens when C is 1 and D is 0. I'm not saying it always happens. I'm not saying you can always read it off, but sometimes you can. And this is one case where it's easy to do that. Well, easy is relative here, but there it is. And now that that's done, integration is trivial. You can just read off what the antiderivative is. Antiderivative of that. Antiderivative of that. Plus some arbitrary constant. And there it is. Was the second integral just a u sub? Very nice, Ethan. Very nice. A u sub, u equals x squared plus 1. Absolutely. Questions? I think we have time for at least one more, maybe two. Questions? Anybody? No? We're good? All right. Let's look at the integrand. My question to you is, how does... Very nice, Amir. Very nice. My question was going to be, how does this decompose into partial fractions? And you notice no real roots. Ethan has pointed out that the denominator has no real roots, so the denominator is irreducible. So this would decompose as ax plus b over x squared plus 4x plus 13. And a is 1 and b is 0. You're already in partial fraction form. And it's important for you to realize that. You don't want to waste any time on an exam applying partial fraction decomposition when you're already in that form. And here you're already in partial fraction form. So applying partial fraction decomposition isn't going to do anything. It'll bring you back to where you were. But Amir has given us the answer already. By suggesting to complete the square for the denominator. And the denominator, when you complete the square, this is x plus 2 squared, which gives you an x squared plus this times 2, giving you the 4, plus 4, but you had a plus 13, so you're missing 9. Very nice. And now we're going to do a u substitution. U equals x plus 2, so that du is dx. And so this becomes, let's change the limits while we're here. 2 to 3. X is u minus 2. This is u squared plus 9 du. Nice to see you again. And now you can split that up. Amir is suggesting a tangent substitution. How is the square completed, right? What are we looking for? We're looking for an x plus a squared, so that when you square this, you get the first two terms. So this is x squared plus 2ax, right? So the x squared is what you wanted. You get a 2ax, but you had a 4x, so 2a is equal to 4, a is equal to 2. And then, very good. And then you square it, and you see that you get a plus 4 in the end, but you had a plus 13, so you're missing a 9. I think Amir had suggested a tangent substitution here. And nothing wrong with that. You can go ahead immediately with a tangent substitution. What I like to do, I like to break it up into two pieces before doing that. Can we do another decomposition with the u? Tempting, but u squared plus 9 is already irreducible. So this will have the form au plus b over u squared plus 9. So it's already in partial fraction form. So again, you don't want to waste any time trying to decompose it. It's already there. Now I like to break it up into two integrals, and you see why. Do you see why? Because this first one, anyone? The first one is just a u sub. Thank you, Dan. The first one is just another u substitution. V equals u squared plus 9. So that dv is 2u du, and u du is exactly what you have here. Very nice. So here we'll make a v substitution. Here we'll make the tangent substitution as suggested by Amir. Here u is 3 tangent theta, so that du is 3 secant squared. Let's change the limits while we're here with this v substitution. When u is 2, v is 13. And when u is 3, v is 18. And this becomes 1 over 2, 1 over v dv. And for this one, let me leave the limits in terms of u. And we get 3 secant squared over 9 tangent squared plus 9. First integral is trivial. 1/2 ln v between 13 and 18. Here, factor out a 9. You get 9 tangent squared plus 1. But tangent squared plus 1 is? Tangent squared plus 1 is? You know what it is. Tangent squared plus 1 is secant squared. Thank you, Amir. Secant squared. So the secant squareds will cancel. And you just get a 1 over 3. So this is a minus 2 over 3 d theta. So 2 over 3 theta. And theta is arctan of u over 3. And the limits were in terms of u, so we can just plug that in. Arctan of 1 is pi over 4. And 2/3 arctan of 2 over 3. And I don't know what that is. How did we know to take u as 3 tangent theta? This is from the ideas developed in the trig substitution section, right? When you have something like x squared plus a squared, you take x to be a tangent theta. And that's exactly what we have here. When subtracting ln of 18 minus ln of 3, it is the same as ln of 18 over 3, right? By properties of the log or log of a over b is log a minus log b. How are we doing? Questions? All right, well, thank you all for coming. For those of you who have joined us expecting 263, I'm going to stop this feed here and start a new one for 263. Could we not keep the simplest form? I'm not sure what simplest form you're referring to, Sam. I am not a fan of the snow at all. I would much rather be somewhere warm right now. Normally I would have said Florida, but with that whole Trump business happening, I think we're going to have to boycott the States for a while. Cancun on the 3rd. Good for you. Did you plug in pi over 4 because you know tangent of pi over 4 is 1? Exactly that. Absolutely. All right, folks. So have a good weekend. I will see you next week. Arthur, well, I mean, the algorithm does not lie. This is where you want to be. Have a good one, folks. And again, for those expecting 263, I'll start the feed right now. Thank you. If YouTube allows me to download that, I will, and put it on my courses. Otherwise, it will disappear forever. Have a good one, folks. I'll see you next week.